Um, Good morning, everyone. My name is Chengpei, and I'm from the School of Mechanical Engineering at the University of Leeds. Today, I'm going to present our research on enhancing sighting to the turbulent lifted hydrogen jet flames. Sorry. To begin, I would like sorry. To begin, I would like to sorry. This now. Oh, it's not okay. Go up, yeah. Sorry. Oh, it's okay. To begin, I would like to introduce about this study. I used COSA-10 to simulate a hydrogen jet diffusion flame, and understanding the behavior of turbulent hydrogen jet flame is crucial for several reasons, particularly in optimizing combustion efficiency, control and controlling emissions, and oh, sorry, it's not this page. Sorry, and enhancing the performance of the combustion devices. However, studying these flames present unique challenges, especially in accurating determining lift of height due to the low visibility of hydrogen flames compared to hydrocarbon flames. Our study aims to conduct a detailed numerical analysis of turbulent lift hydrogen flames. We will explore various pipe shapes, size, and jet velocity, compare our computational results with experiment data to explore our understanding of the underlying dynamics. And yeah, turbulence model. As for the turbulence model, we choose the LR model. It's a second order Reynolds stress model, particularly suited for computing the anisotropy of turbulence in free jet flows like circle jets. The valve average NS equations coupled with energy equation were used to compute the velocity and temperature fields. Additionally, we employed the second order closure to determine turbulence heat flux, in allowing us to accurately model the complex intentions between fluid dynamics and the chemical kinetics in hydrogen jet flames, and to model the combustion process. We use the mixedness and the directness Fleming model. Initially, it's a model developed for methane, but adapt for hydrogen. In our study, this model allows us to compute the mean heat loss rate by integrating laminar flamelets with detailed chemistry into the turbulence flow, and we employed assumed the beta probability distribution functions for mixedness, along with a Gaussian distribution of strain rate to consider the effect of turbulence stretch at the flamelet. This approach enable us to strike a balance between computational efficiency and accuracy, making it suitable for the complex 3D simulations required for our analysis. And also, our computational task was carried out using CodeSaturn, advanced open source computational fluid dynamics software developed by Electricité de France. Version 8.0 of the code incorporate various turbulence models, including in Reynolds stress equations and turbulence heat flux equations. The combustion model was integrated into the software through user-defined subroutine. Our simulation were fully 3D and time-dependent with computation domains of specific pipe dimensions and jet exit velocities. The setup ensure that our simulation captured the full development of the flame dynamics. And here is the video of one of the simulations. The jet pipe diameter was 2.9 millimeters. The jet mean velocity was 500 meters per second. Reynolds number was around 13,000, and times is from 2.4 second to 2.75 second, and it's a surface of 10 million watts per meter cubed surface. And the mesh size depends on the flame length, and from the literature, and the maximum mesh size is around 3 times 3 meters times 3 meters times 7 meters, and it's around 4 million. Mesh is around 4 million cells, and the time steps is around minus 10 minus 5 to 10 minus 4 per second. Sorry. And here is the present the 2D flame counterlines of a turbulent hydrogen jet flames at different jet exit velocity at as observed, the flame structure varies significantly with changes in velocity. At 300 meters per second, the flame appears relatively compact, whereas at 763 meters per second and 1,200 meters per second, the flame becomes more elongated and dispersed, and this indicates the higher jet velocity result in a longer and more diffuse flame, highlighting the direct impact of velocity on flames. And here is the slide displays a 2D heat rate counterlines for different jet velocities. It's evident that there are difference in heat rate distribution between 500 meters per second and 1,000 meters per second cases. The higher jet velocity of 1,000 meters per second leads to a lower maximum heat rate, suggesting that the combustion process inhibition with higher speed, producing less heat. Also, the heat release positions are different under higher and lower speed conditions. The heat release position of high-speed flame is close to the jet front, and the for the lower velocity is like in the two side near the pipe, and the results underscores the significant influence of velocity on the intensity of the combustion process. And this slide shows the analysis of key parameter at the base of the turbulent lifted hydrogen jet. Specifically, they illustrate the distribution of mixture fraction, mean strain rate, and the velocity overlaid on the mean volume heat rate counter field. This result is at the flame blaze with regions of high different suitable strain rate and mixture fraction correspond to more intense combustion. The velocity distribution further indicates the role of turbulence in influencing the combustion process at the flame base. And also here is simulation results for triangle pipe. For the triangle pipe, you can see the heat rate is much closer to the pipe itself. The position of the at the corner is much closer to the pipe, and the velocity at the corner is much higher because of the streamline. You can see, and yeah, here is the results for the analysis of lift of height of flames under different conditions. It shows the lift of height measured under 800 K and different heat rates, and the hydrogen flames is invisible and not invisible, but it's hard to see. So the experiments always use different conditions to measure it, but it's not accurate enough because visible is hard to define. However, the luminous characters of hydrogen flames are closely associated with the concentration of the excited state of OH within in the flame. So there is a correlation between the OH star and heat release rate. So I can use heat release rate to define lift of height and flame length and compare with the experiment. Here is the results for different shapes of the pipe exist. As you can see here, I also use the 800K as to measure the lift height, and use the 10 milliwatts per meter cubed to measure the lift height. And as you can see, the circle, the lift height of the circle pipe is lower, and all the different condition to measure makes the same trend of the lift of height. And the higher the jet velocity, the higher the lift of height here. And here is a results for different pipe diameters. For pipe diameters, because the case before is diameter 2.9 millimeter, and for the diameter 1.8 millimeter, you can see the lift height is much low, is much lower. And yeah, so the more the pipe diameter, the lower the lift height. And here is the flame length. Also, I compared the flame length of different heat release rates, and I find also the 10 milliwatts one heat release rate is closer to the experiment data. So I use it to measure the flame length, and the different shapes give me also the circles flames. The flame from the circle pipe gets the lower flame length. And also I just here is the shape of the flame root of different shapes. It's triangle. For A is figure A is triangle exists. For figure B is a rectangle exists, and figure C is a square exists. At left side is 500 meters per second, and the right hand is 1,000 meters per second. The higher the velocity, the shape is much closer to the circle. But in a low velocity, it's not. It remains the shape of the pipe. And here is the sphericity of the different pipe exists, as you can see. Okay, and yeah, his conclusion. In conclusion, our study employs a Reynolds stretched family model to provide a comprehensive analysis of turbulent lifted hydrogen jet flames. By comparing our computational results with experiment data, we have validated our model and gained new insight into factors that influence lift height and flame stabilization. Notably, we found that the shape of the pipe outlet and jet velocity significantly affects the lift height and flame length, with circle pipes producing smaller lift of height and more stable flames compared to other shapes. Okay, and I would like to extend our graduate to University of Leeds for providing access to computer facility, and to the TFSC for granting access to SCARF computing resource. Yes, and here's a detailed reference.
Okay, many thanks, Chengpei.